Oh, nice. Yeah, we can see it.
Nice, perfect.
Ready?
Yes. Okay, then first, welcome to my presentation. And the topic is, as you can see my automatic annotation of Chinese Suzipu notation using a component-based prediction and similarity approach. This sounds a bit complicated. It is a bit complicated, but we will go through the details, so it will, at the end of the session, not be so complicated anymore. Okay, just a short roadmap. First, a short introduction. Why are we doing this? What are our goals? Then we will talk about the classification problem of the Suzipu notation, which is a Chinese kind of notation. Then we will talk about similarity and clustering, about intelligent selection of previously annotated samples, and finally, the integration of these into an intelligent user interface called the annotation tool. So let's get right into the matter. In 1202, the poet Zhang Hui wrote and published a collection of poems, which is called Baishidao Guzhu, and this translates to the songs of the white stone Taoist. And this is the largest historical source of a notation we call the Suzipu notation. And it is related to other Chinese notations such as the Gongchepu notation, which is, for example, still in use in many Chinese musical theater traditions like Cantonese opera, for example. And the interesting thing is, even though it is a poem anthology by modern perception, in reality, most of the poems are of a certain kind called zi, and this used to be a sung form in 1202 in the Song dynasty, and only later in the subsequent centuries it became a rather purely literary genre. So indeed, it contains one of the earliest melodized Chinese lyrics we have in total about all of Chinese music history. And in our work, the Quasima dataset, this is from the name, of course, inspired by other famous datasets like the Musima. And we have 5 different handwritten editions of the Speicherdaring Guzhu. And they range from 1736 circa to 1930. And you know, the original was published in 1202, but the originals have been lost for some centuries. So these editions are the only ones we have from these time periods. There are some other that are not yet included, but this is work in progress. And it contains in total 3 different notations, not only the aforementioned Suzipu, but also Lülipu, which is some kind of ritual music notation, so to say. And this is also, in fact, in a similar manner used like the Korean notation that was in the keynote, which David presented. This is a bit similar. And also Jianzipu, which is a tablature for a string instrument called Wuqin. So it's like the ancient guitar tabs of China in some way, except that only very scholars could usually play it. And the dataset contains in total about 74,000 manually checked annotations, and 50.5% of those are musical notations. It is on a character level base with bounding boxes, and in total, 511 of those pages of these editions are annotated. But here we're only focusing on the Suzipu part, and here we have roughly 7,500 annotations. So this is a very small data set, and we will see what the problems with it are. So let's dive into the classification task. So basically, in the Suzipu notation that Zhanghui uses, there are two components: a mandatory pitch component, which consists of 11 symbols, and an optional secondary component, which consists of 6 symbols, or because it's optional, non-symbol. And the problem is that when these are combined, the problem is difficult. Like just the pitch symbols, it is very easy to get very low error rates of maybe up to 2%, character error rate, like speaking. But whenever the secondary components come, it's much more difficult because we now have 77 possible symbols in total. And because the original symbols were written with brushes on paper or then carved out from a wood block, usually the symbols are sometimes connected like with brush strokes. So it is not very simple to separate them often. And also human annotators might have problems, but this is yet to be verified in the user study. And so you can see we have little data, but 77 classes actually. And about the optical music recognition, we have proposed the first baseline, which splits it up by pitch and secondary components, which is sometimes done in cases of limited data and where the data space can be modeled like this kind of product space. And with this, for both components in total, we get a character error rate of around 10.4%, which is not that well yet. So there is still potential for improvement. And basically, it's just a simple CNN for now. And with this, the prediction is then made into a simple classifier for each component. And here we have this FC2 layer, which is a 120-dimensional vector. And we need to remember this for the next few slides, that there is some kind of internal representation. And also because it's a classifier that has sometimes problems with interpretability, we endow the model with a temperature scaling calibration. And this means the model predictions are not affected, so the character error rate stays the same, but the model output is in the quantity corresponding to the model accuracy. For example, you can see here the uncalibrated model. And ideally, if a model was perfectly calibrated, the class output would correspond to the actual probability of it being a correct representation. And here you can see that this model, for example, is overstating its confidence. For example, if we have a confidence of around 70%, we only have an actual accuracy of 60%, and this is not desirable. So using the calibration, where we calibrate the softmax by a temperature scaling factor, for confidence levels of above 50%, we get quite a good approximation. So whenever the user uses the model, for example, in the user interface, they can know how much they can trust the model. And if the confidence is below 50%, they should not trust the model at all, because it could be anything. So now let's go to the similarity and clustering. And here, because we have this product space, we have a special problem of continuous data spectra. Of course, the notation classes are discrete, but the image data is always continuous in this setting, so to say, even though it's discretized in this pixel level. And we can see that sometimes it's not very clear. There is not a clear boundary between the annotations themselves. As you can see here, for example, this goes through in total 3 different annotations, depending on the exact values. And now I need you to remember the FC2 level, which was a 100-dimensional vector, because with this, when we take this as our model output in this case, we have a feature representation for both the pitch and for the secondary models. And with a UMAP or maybe some other clustering approach, we can then get coordinates for this in a 2D space, which we can then visualize more easily. And in this case, we can see the UMAP space where the clusters are determined by the model and the color annotations are corresponding to the true labels of the annotation of the annotated images. For example, like the symbol S would be here, but it bleeds a bit into this other cluster because sometimes it can be similar to gong, as we can see here. It's just when this part of the annotation in the image data is missing, it would be classified as gong. But you can see in total, the separation is not so bad for the pitch embeddings. On the secondary embeddings, it's a bit more difficult because only around, I think, 15% of the total data are these composed symbols. The majority is the pitch symbols. And here we can see the non-class. This is very, very much. So this contains also a bit of information about the pitch annotation. But of course, it separates according to the secondary information because this is from the secondary classifier. And yes, here we can see some things are quite easy to detect. For example, this ja annotation, even though sometimes it bleeds into the yeah. But in total, this is also, for the first baseline, an okay result. Of course, there's potential for being better. But we want to incorporate these features now to help users that have to manually annotate this kind of music to annotate it more efficiently and better in total. And for this, we have also another feature, which is the intelligent selection. Because maybe you know it when you annotate something, sometimes it is similar when you annotate the same corpus in different editions, that you look at reference samples from the same corpus, for example. So you're not sure this is an annotation, but you don't know what is it. So you have maybe a suspicion, you annotate it, and then the model can propose you some images that have the same annotation, but you know they're already correctly identified, so you can compare. And in case there are only up to 39 samples, it's easy. Everything is displayed. But otherwise, because some classes have more than 400 annotations, this is impossible for a user to comprehend. So there is a clustering algorithm acting on the image data and then separating it into 39 classes where one random representant is chosen. And when we look at this, how it's integrated, we can see, for example, let's start with the last one, the similar annotations. So we have already set, this is the annotation, and here it displays other similar annotations that have the same annotation, but of course from different editions and so on. So as a user, it might be helpful. Then with one, we can start the optical music recognition model, so to say. And when we are content with it, we can override our annotations in the tool to save eventually. And here we can see the pitch prediction, including the confidence calibration. And in this case, it is very clear. And according to the clustering, we also see which is regarding pitch component and secondary component, the closest neighbor in this UMAP transformed space. And with this, we have to, or at least we hope that this can annotate, that this can help annotators annotate better and more efficiently. And I can only now tell from my experience, because I have annotated 75,000 of those annotations in total. And for me, it helps. But of course, the next step in the future work is to verify in a real user study with some individuals so we can check how much it really helps and if they prefer it to no intelligent assistant, for example. Yes, and with this, I want to say thank you for the attention. And of course, the data set, the code, and everything you can find in this GitHub repository of the QR code. And I haven't stopped the time, so I don't know if there's still time for questions.
Yes, there's always some time for questions. Thank you, Tristan, for the talk. Any questions? Okay, Alex, go ahead.
Yeah, I have one question. Maybe I didn't catch it. When you showed the model, and you said you have two different kinds of outputs, the primary and the secondary classification. How do you model this in there? Do you actually have two classification heads of the model? Or do you combine it into one combined vocabulary and have more classes?
Yes, actually, right now it is done with two separate heads. So really two separate models are trained. And it is made this way that the data is sampled so that on each component we have uniform distribution. And this yields for now the best results. But I've also tried in a study to combine these two heads into one model because I was thinking maybe if two models get the same convolutional output in the intermediate layer, it would perform better. But it showed somehow, maybe I haven't found the right calibration yet, it's still a process, that when I sample each of the 77 classes uniformly, including some artificial data where classes that do not appear in the data are also present, it has much longer training times. And also the accuracy is not that of the simple models of the two. So yes, for now, this is the best solution. And for me, it's a bit counterintuitive because I was thinking the more information there is for both models, maybe the better it would get. But it can also, of course, be that the hyperparameters are still not optimal for the task.